Hey everyone, welcome back to Info 3370, studying social inequality with data science. Today we'll be discussing causal assumptions. Our learning goals are to formalize causal assumptions in directed acyclic graphs, and to use DAGs to find a sufficient adjustment set of variables within which a given statistical association answers a question we have about some causal effect. So what is a directed acyclic graph? A DAG is a formal graph used for causal assumptions. In a DAG, there are nodes and edges. Each node, here A, B, and C, is a variable. For instance, A might be whether I went to college, taking the values yes or no. Each edge is a causal relation. In this case, A affects B, B affects C, and A affects C directly. For example, perhaps C is my earnings, and what this would say is that an intervention to send me to college might change my earnings. And that has to be true for at least someone in the population for there to be this arrow from A to C. So a causal directed acyclic graph is directed in the sense that every edge has an arrow. Causality here flows in one direction. And a DAG is also acyclic, meaning that there are no cycles. So to illustrate what I mean, these two graphs are not DAGs. The one at the left is not a DAG because there's no directions on those edges. The one at the right is not a DAG because it has a cycle, from A to B to C and back to A. Cycles are not allowed in these causal graphs. And that might seem odd to you because you might think that we care often about social processes that have feedback loops. If you're studying feedback loops, you can often create a DAG with no cycles by simply stretching that out over time, so that you have A at time 1 affects B, affects C, affects A at time 2, which is a new node in the DAG. Those types of DAGs are beyond the scope of what we'll cover in class today, but they illustrate how DAGs are a quite general tool that addresses lots of causal problems. Why draw a DAG? DAGs are great because causal assumptions become both visually intuitive and mathematically precise. To illustrate, suppose we're examining the causal effect of attending college on your future earnings. Perhaps those two variables are associated in part because sending someone to college will cause them to earn more down the road. But that's not all that's going on. Perhaps those who do well in high school end up going to college. And maybe your high school performance would have a direct effect on your earnings regardless of whether or not you attended college. Thus, perhaps the people who go to college have higher earnings, not because college causes their higher earnings, but because those people tended to have high school performance, which in turn caused them to have high earnings. The story doesn't end there. Perhaps your parents' education affects your high school performance. If your parents went to college, they might help you get into college. They might also have connections to people who could help employ you, thus causing you to have higher earnings. And we might also think that race, through processes of structural racism, affects the quality of your high school, thus your high school performance, and through historical processes of racism might constrain your parents' education. Race may also play a role in where you go to college and whether you go to college, and due to discrimination in the labor market will likely affect your earnings directly. You can see here how this DAG has quickly become complicated. And yet, the DAG is still visually intuitive. I was able to tell you a story about each of these edges and why it's there in the DAG. Further, the DAG is mathematically precise in a way that we'll discuss in the coming slides. It helps us know which causal effects are identified and which ones are not, in a very formal way. The DAG tells us the causal origins of statistical associations. When we think about why the treatment A and the outcome Y are associated, they could be associated by a causal path, such as me finishing college causes me to have higher pay, or through a backdoor path. A backdoor path can involve what's known as unblocked forks and also blocked colliders. So to start with the forks, perhaps your parent finishing college affects whether you finish college, which in turn affects your pay. This kind of forking structure creates an association between A and Y that's not due to a causal effect of A on Y, but rather to the fact that they share this common cause, C, which is an ancestor of both A and Y. We refer to this as a backdoor path. And to keep this in my mind, I like to imagine a house located at the place where the treatment is. That house has a front door and a back door, and we're interested in the causal processes that go on through the front door from the treatment out to the outcome. And we're not so interested in the associations that come through these backdoor paths, where you have to start at the treatment, walk out the back door to a common ancestor, and then out around the house to get to the outcome. Much of what we'll do in this class is think about how to block backdoor paths in order to isolate causal effects. In this case, to block this backdoor path, you could condition on C. Conditioning on C simply means that we'll analyze data within subgroups defined by C. We often denote this in the graph by putting a box around the variable C. I said I would come back to the second kind of backdoor path that can be tricky to think about. This is colliders. So, as an example, suppose that I have sprinklers that operate on a timer. I observe whether the sprinklers are on, x1. I also observe whether it's raining, x2. And finally, I observe whether my grass is wet, y. We say that y here is a collider along the path x1 to y to x2. It's a collider because these arrows collide at the variable y. The collider here blocks the path. If you think in the whole population, there's no association between whether my sprinklers are on and whether it's raining. After all, the sprinklers just come on every day at the same time. In this case, x1 is independent of x2. Yet conditioning on y opens up a statistical association through this path. Once I know that the grass is wet, then I know that either the sprinklers have to be on or it's raining. This is what can be tricky about colliders. They don't create an association when they're left alone, but as soon as you adjust for that variable, the grass being wet, you create an association between x1 and x2. One of the reasons that DAGs are super helpful is because they help us think about distinctions between variables that are ancestors and variables that are colliders. Both an ancestor and a collider are connected to the variables of interest through paths, but the directions of those paths operate in the opposite directions. Conditioning on an ancestor closes an open path, while conditioning on a collider opens a closed path. Our two examples here are on the left, your parents' education affect your education and your pay. We would want to adjust for parents' education. On the right, whether the sprinklers are on and whether it's raining both affect whether the grass is wet. And in this case, looking at only the subset of times when the grass is wet can produce really confusing conclusions. In the population, the treatment and outcome are related through paths that involve an ancestor, and they're independent through paths that involve a collider. But when you adjust, then these two properties reverse. This is all important because the reason we've talked about these processes is because we really want to understand what variables we should hold constant in order to isolate the causal effect of a variable of interest on an outcome. In this case, we want to know the degree to which college causes earnings. Between college and earnings are many paths. There's the causal path, represented in blue, and there are also a zillion backdoor paths. There's from college back to high school performance out to earnings, college to high school performance to race, around to earnings. You can trace a bunch of them. And we have to think about what we could hold constant in this model to block all of those backdoor paths. When blocking the paths, we want to block paths involving an ancestor, but we don't want to condition on colliders that will open new paths. So to practice this, let's think quickly about some rules for finding an adjustment set of variables that can identify a causal effect. As I said, our goal is to block all the backdoor paths, so we just have the causal path left. A backdoor path is any sequence of edges that at the ends point into the treatment A and into the outcome Y. That path is blocked if it contains an adjusted variable along some fork path, and it's also blocked if it contains an unadjusted collider variable. So now in class, we're going to discuss 3 exercises. In class, we'll all work on these in groups and then talk about them together, but I'll just go through them quickly in the video here. In this DAG, we want to find adjustment sets that identify the causal effect of the treatment A on the outcome Y. Between these two variables, there's just one backdoor path. A back to x1, out to x2, to x3, and over to y. We can block that path in several ways. We could condition on x1. We could condition on x2. We could condition on x3. We could condition on any combination of x1, x2, and x3. Any of these strategies equivalently blocks the path, so that the only reason A and Y would be associated once we adjust for x1, x2, or x3 is the causal effect of A on Y. Next, we could find 3 sufficient adjustment sets to identify the causal effect of the treatment A on Y in this DAG. In this case, we could adjust just for x2. Once you hold x2 constant, there's no path back from A to Y. You might worry that x2 is a collider. Adjusting for it creates an association between x1 and x3. But because these variables are independent of A, once we condition on x2, then that actually doesn't matter that creates an association. We could also condition on x1 and x3, or we could condition on all 3 variables together. Finally, let's try to think about what's the smallest adjustment set that identifies the causal effect of the treatment A on the outcome Y in this case. Here we might be worried about the backdoor path from A back to x3, down to x2, back to x1, and out to y. What's the fewest number of variables we could adjust for to identify the causal effect of A on y? In this case, we actually don't have to adjust for any variables at all. That's because this backdoor path is already blocked by the presence of the collider x2 along the path. In fact, if you adjust only for x2, you would create an association between x1 and x3, just thus opening a path that was previously blocked. This is a nice example to have in mind, because you might run into other people who will tell you that you should adjust for all the variables that temporally precede the treatment. But here, x2 might be one such variable. And yet if you adjusted for only x2, you would get worse estimates than if you had simply looked at the marginal association between A and Y. This is why drawing the DAG is super helpful, because it helps us see exactly which variables we should adjust for and why, given the causal assumptions that we've encoded in the DAG. So that's it for today. Our goals here were to formalize causal assumptions in directed acyclic graphs, and to use those DAGs to find a sufficient adjustment set of variables within which a statistical association is causal. DAGs are the backbone of empirical research in the search of causal effects from observational data, and they're an extremely useful tool. Of course, at the end of the day, your inference is only going to be as good as the assumptions in the DAG. What the DAG buys you is that it says if you buy into these causal assumptions formalized in the DAG, then the statistical evidence supports a causal conclusion. Of course, if your DAG is wrong, then your conclusions aren't going to be good either. So that's why DAGs are great. They help us reason about the causal assumptions underlying our evidence, and they let us have those arguments to figure out what we're willing to assume and thus what we can conclude causally.